Welcome to the Deep Sleep Science Channel. Tonight, we're drifting into a universe where a storm can grow larger than a planet, where a city-sized star can outweigh entire worlds, and where light has been traveling for over 13 billion years just to reach your air. Eyes. Out there, moons can hide oceans beneath ice. Tiny fragments of rock can carry the ingredients of life, and invisible forces shape galaxies across distances too vast to truly imagine. The deeper we look, the strange and more beautiful space becomes. So, settle in, relax your mind, and let these quiet discoveries carry you gently through the cosmos. And if you find yourself enjoying the journey, feel free to like, subscribe, or leave a comment before you drift off to sleep. A neutron star is one of the densest things astronomers can directly observe, and that becomes even more astonishing when you picture what that really means. This is the collapsed core of a once massive star, packed so tightly that matter is squeezed into an almost unimaginable state. It is not just heavy in an ordinary sense. It is a kind of density that pushes far beyond everyday experience, turning a stellar remnant into something so extreme that it feels almost unreal. NASA describes a typical neutron star as roughly 500,000 Earth masses compressed into a sphere only about 12 miles, or around 20 kilometers across. That means an object no wider than a city can hold more mass than countless worlds put together. It is one of those rare scientific realities that sounds exaggerated at first, yet it is a serious part of modern astronomy, and one of the clearest reminders that space does not follow human-scale intuition. Because of that compression, a city-sized neutron star can outweigh entire planets by an astonishing amount. The mind wants size and weight to match in a familiar way, but in space, they often do not. Something small can be overwhelmingly massive, and something vast can be strangely thin or empty. A neutron star is one of the best examples of how the universe quietly breaks the visual rules we expect. A moon can be bigger than a planet, and Titan is the perfect example, since it is larger than Mercury. That sounds backward at first, because people often imagine planets as automatically larger than moons. But nature does not arrange objects by category in neat human ways. Titan is still a moon because it orbits Saturn, yet in sheer size it surpasses one of the official planets in our solar system. A storm can be larger than a planet, as Jupiter's great red spot is larger than Earth. This is not a small storm magnified by dramatic language. It is a true atmospheric giant, a long-lived system swirling in the clouds of Jupiter on a scale that makes Earth look modest by comparison. The idea that weather itself can grow larger than a world gives Jupiter a kind of grandeur that feels almost impossible. A black hole's shadow can be compared to the size of a planetary orbit, and the shadow of Sagittarius A** spans about half the diameter of Mercury's orbit. That means the dark silhouette associated with the Milky Way's central black hole is not merely a point or speck in space, but something with a scale that can be measured against the paths of planets. Even more striking, this enormous feature belongs to an object that lies tens of thousands of light years away from us. Webb is designed to look back more than 5 billion years toward the first galaxies, which means it is studying light that has been traveling through the universe for nearly all of cosmic history. In a real sense, this telescope is not simply observing faraway objects. It is looking into deep time. The farther it sees, the younger the universe appears, so its images help scientists study eras that existed long before Earth or the Sun even formed. A telescope can need something as simple in principle as shade, yet Webb's shield must block enough heat from the Sun, Earth, and Moon to let it detect ancient infrared light. This is a beautiful example of how advanced science sometimes depends on a simple idea carried to an extreme degree. To see faint warmth from the distant universe, The telescope itself must stay extraordinarily cold and protected. NASA compares the effectiveness of Webb's sunshield to SPF 1 million, which is a vivid way of describing just how strongly it blocks incoming heat. Of course, this is not sunscreen in the everyday sense, but the comparison helps translate a complex engineering achievement into something easy to imagine. The result is a telescope that can remain cold enough to do a job no ordinary warm telescope could manage. Voyager 1 and Voyager 2 are the only spacecraft ever to operate outside the heliosphere, which is the Sun's broad bubble of influence in space. These machines were launched by humans from Earth, traveled for decades, and eventually crossed beyond the region dominated by the solar wind. That means they are not just far away. They are exploring the boundary between our solar neighborhood and the wider interstellar medium beyond it. A spacecraft launched in the 1970 can still help measure the frontier between the Sun's influence and interstellar space. That alone feels almost unbelievable. These missions were designed in an earlier technological era, yet they remain scientifically useful after more than 4 decades. Their continued work shows how durable engineering, careful planning, and the emptiness of space can combine to create missions with lives far longer than anyone casually expects. Rosetta discovered a kind of ultraviolet aurora at Comet 67P/Churyumov-Gerasimenko. Auroras are often associated with planets, especially with worlds that have strong magnetic fields and thick atmospheres, so finding an auroral process connected to a comet expands the imagination. Even a small icy body, irregular in shape and far from being a full-sized planet, can participate in energetic interactions with light and particles in surprising ways. That discovery means auroral processes are not limited to planets with strong global magnetic fields. In other words, the universe is more flexible and inventive than the simplest classroom picture might suggest. Phenomena we first learn in one setting often appear again under very different conditions, shaped by different environments but still following the same deep physical principles. Haumea is unusual not only because it is a dwarf planet, but also because rings have been found around it. Rings are often imagined as the special signature of giant planets like Saturn, yet here they appear around a much smaller, distant world. That makes the outer solar system feel richer and less predictable, full of bodies that do not fit neatly into the categories people first learn. Chariklo, a much smaller object known as a centaur, also has rings. This is another reminder that space regularly takes familiar patterns and places them in unexpected settings. A body does not need to be a major planet to host a delicate ring system. Even relatively small worlds can carry around narrow structures of orbiting material, quietly rewriting our sense of what kinds of objects can be complex. Neptune is the first planet discovered through mathematics before direct observation confirmed it. That means scientists were able to infer its presence by noticing subtle irregularities in the orbit of Uranus and working backward from those clues. Long before a telescope revealed the planet clearly, calculation pointed to where it should be. It is one of the most elegant examples of reason and observation working together in astronomy. Space itself can stretch, carrying galaxies away from one another as the universe expands. This is not simply galaxies flying into empty space the way sparks scatter in air. Instead, the fabric of space between them grows. That is one of the deepest and strangest ideas in modern cosmology, because it changes how distance itself behaves on the largest scales. Dark matter is invisible, but astronomers infer its presence because it helps hold cosmic structures together. Scientists do not see it shining or glowing the way stars and gas do. Instead, they detect its influence through gravity, through the motions of galaxies and other large structures that do not make full sense if only visible matter is counted. It is one of the strongest examples in science of learning about something by the traces it leaves behind. Dark energy is associated with the accelerating expansion of the universe. So the cosmos is not only expanding, but doing so in a way that appears to speed up over time. That is one of the great modern discoveries in astronomy, because it suggests that the universe is shaped by a major ingredient we still do not fully understand. Current NASA summaries put dark energy at roughly 68.3 to 70% of the universe. That means the largest share of the cosmos is attributed to something that does not behave like ordinary matter and is known mostly through its large-scale effect on expansion. It is a humbling fact. The dominant component of the universe is not something humans can point to directly in the sky with their eyes. One of the strongest patterns in astronomy is that the closer scientists look, the less empty and less simple space becomes. A dark patch becomes a galaxy field. A distant point becomes a world with weather. A moon becomes an active place with chemistry and geology. Again and again, better instruments reveal that space is richer, busier, and more structured than earlier generations imagined. The observable universe contains galaxies, stars, planets, gas, dust, black holes, and many other structures across immense scales. When astronomers talk about the observable universe, they mean the region from which light has had time to reach us since the beginning of cosmic expansion. Even that reachable portion is staggeringly full. It is not a simple spread of isolated stars, but a layered cosmic landscape containing objects and systems of many kinds. Galaxies are gravitationally bound systems made of stars, planets, and vast clouds of gas and dust. They are not random collections of objects drifting together by accident. Gravity helps organize them into large, enduring systems, where stars are born, evolve, and die, and where dust and gas continue to shape future generations of structure. A galaxy is, in many ways, a whole ecosystem of matter on a tremendous scale. The largest galaxies can stretch more than 1 million light-years across. A light-year is the distance light travels in a year, and even 1 light-year is already enormous by human standards. So when a galaxy grows to more than 1 million of those units across, the scale becomes almost too large to picture. It turns a single galaxy into something that feels more like a cosmic region than a simple object. The smallest galaxies can span only a few hundred light-years and contain just a few thousand stars. That means galaxies exist across a huge range of sizes, from immense giants to small, faint systems that are tiny by galactic standards. Even these smaller galaxies still matter deeply to astronomy because they preserve clues about how structure forms and evolves in the universe. The Milky Way is a spiral galaxy, which means it has a broad disk with curving arms wrapped around its center. Spiral galaxies are among the most visually striking structures in astronomy, with their sweeping patterns of stars, gas, and dust. From inside the Milky Way, we cannot step back and photograph the whole shape directly, but many lines of evidence show that our home galaxy belongs to this graceful family. Our solar system lies in a small branch of the Milky Way called the Orion Spur, between the Sagittarius and Perseus arms. So even within our own galaxy, we are not sitting at the exact center of a grand arm, but in a smaller structure between larger ones. This gives a useful sense of placement. Earth is not only part of a solar system, but also part of a specific neighborhood within a much larger galactic design. Most large galaxies appear to host supermassive black holes at their centers. This means giant black holes are not rare oddities limited to a few unusual systems. They seem to be a common feature of galactic structure, deeply tied to how galaxies grow and behave. In many cases, the central black hole and the galaxy around it appear to have evolved in connected ways over immense spans of time. The supermassive black hole at the center of our galaxy is called Sagittarius A*. This object anchors one of the most dramatic regions in the Milky Way, even though we cannot see the black hole itself, in the ordinary sense. Its presence is known through the motions of nearby stars and other careful observations, making it one of the best-studied black holes in the sky. Sagittarius A* is about 4 million times as massive as the Sun. That number helps explain why the center of the Milky Way is such a powerful gravitational environment. A black hole with millions of solar masses is not just large in a casual way. It is a deep gravitational well, shaping the motion of matter and stars in the galactic core. Even though Sagittarius A* is the Milky Way's central black hole, it still lies more than 26,000 light-years from Earth. So when astronomers study it, they are examining something both central to our galaxy and yet still astonishingly remote from our everyday location. The center of our own galactic home is far beyond any ordinary journey humans can imagine. The cosmic microwave background was released about 375,000 years after the universe began. Before that time, the young universe was too hot and dense for light to travel freely over long distances. Once conditions changed enough for atoms to form and space to become transparent, that ancient light began its long journey. Today, astronomers can still detect it as a faint glow spread across the sky. Tiny temperature differences in the cosmic microwave background acted as seeds for later cosmic structure. These differences were extremely small, but they mattered enormously. Regions with slightly more matter had a little more gravity, which helped them pull in additional material over time. From these subtle beginnings, the large structures of the universe gradually emerged. Those early fluctuations eventually helped matter clump into stars, galaxies, and galaxy clusters. In that sense, some of the biggest structures in the universe trace back to tiny unevenness in the early cosmos. It is one of the most beautiful patterns in science. Small differences, given enough time and gravity, can grow into immense and complex forms. The modern picture of the cosmos includes both visible matter and large, unseen components that dominate its total content. Stars, glowing gas, planets, and dust are only part of the story. The broader cosmic balance includes dark matter and dark energy, which do not present themselves in ordinary visible ways, yet appear to shape the universe on the largest scales. Our solar system includes 1 star, 8 planets, 5 officially recognized dwarf planets, hundreds of moons, and huge populations of asteroids and comets. So even the system we call home is not a simple arrangement of a sun and a few planets. It is a layered family of worlds, icy bodies, rocky leftovers, and orbiting companions, all shaped by a long and dynamic history. NASA's Solar System Summary once listed at least 290 moons in one overview, while later moon-specific updates pushed the confirmed total much higher. This is a good example of how astronomy changes as observations improve. New moons are found, classifications are updated, and the official portrait of the solar system becomes more detailed over time. As of March 25, 2025, NASA reported more than 891 confirmed moons in the solar system. That number is far larger than many people expect when they first think about planetary systems. It reminds us that planets are not the only important worlds. Moons are everywhere, and many of them are complex places with their own geology, atmospheres, oceans, or unusual histories. Most moons orbit planets, but some asteroids also have moons. This widens the idea of what a moon can be and where it can appear. A moon is not reserved for the major planets alone. Even smaller bodies can have companions. showing again that gravity creates systems within systems all across space. Our solar system formed about 4.57 billion years ago from a collapsing cloud of gas and dust. That means the Sun and planets were born from the same broad raw material, gathered and reshaped by gravity over immense time. The worlds we know today are the result of that long process of collapse, heating, spinning, and gradual assembly. The cloud that formed the solar system likely had only about 10 to 20% more mass than the Sun has today. This is a remarkable detail because it suggests that most of the original material ended up in the Sun itself. The planets, moons, asteroids, and comets together account for only a relatively small fraction of the starting mass. Gravitational attraction keeps the planets in elliptical orbits around the Sun. They are not moving in straight lines through empty space with the Sun somehow pulling them back now and then. Instead, their forward motion and the Sun's gravity combine to create stable, curved paths, giving the solar system its lasting orbital structure. The planets are commonly divided into rocky terrestrial worlds and much larger giant planets. This broad split helps describe two major styles of planet in our solar system. The inner worlds are smaller and denser, built mainly from rock and metal, while the outer giants are much larger and dominated by lighter materials. The four inner planets are Mercury, Venus, Earth, and Mars. These worlds occupy the warm inner region of the solar system and share the basic trait of being terrestrial planets. Even so, they are very different from one another in atmosphere, temperature, geology, and history. The four outer planets are Jupiter, Saturn, Uranus, and Neptune. These larger worlds dominate the outer solar system and differ strongly from the inner rocky planets. They are vast, complex systems with rings, many moons, and deep atmospheres that behave in ways unlike the solid surfaces of the terrestrial worlds. The solar system is moving through the Milky Way at about 515,000 miles per hour, or about 828,000 kilometers per hour. Even while Earth spins and circles the Sun, and even while the planets follow their own paths, the entire solar system is also traveling through the galaxy. So our local cosmic home is never truly still. One complete trip by the solar system around the center of the Milky Way takes about 230 million years. This is sometimes called a galactic year, and it shows how different cosmic timescales are from human ones. Entire chapters of Earth's history can pass before the solar system completes even one orbit around the galactic center. The solar system extends far beyond the planetary region. The planets occupy only the more familiar inner portion of a much larger domain influenced by the Sun. Beyond them lie distant reservoirs of smaller bodies and icy objects, stretching the true reach of the solar system far past the paths of the major planets. ESA describes the solar system as extending to at least 150,000 million kilometers from the Sun. That immense distance helps show why the solar system is not just a tight arrangement of planets gathered close to the Sun. It is a broad gravitational realm with outer regions so remote that they challenge ordinary visualization. Yet the major planets are all found within about 6,000 million kilometers of the Sun. So the most familiar large worlds occupy only a comparatively compact part of the solar system. Beyond them, space opens into much larger and sparser regions containing smaller icy bodies and long-period travelers. Beyond the planets lies a much thinner interplanetary medium of gas and dust. Even what people casually call empty space is not perfectly empty. There is still matter there, though spread extremely thinly, along with magnetic fields and moving particles from the Sun. Space can look blank, but physically it remains active and structured. The Oort cloud is also considered part of the solar system. This means the Sun's family of objects may extend into a vast distant shell of icy bodies far beyond the planets. The Oort cloud is so remote and diffuse that it feels more like an outer boundary of influence than a region we can easily imagine visiting. The Kuiper belt lies beyond Neptune and contains dwarf planets and many icy bodies. It is one of the solar system's great outer zones, a region preserving many cold leftovers from early formation. Objects there move in the deep chill of the Sun's distant reach, and they help astronomers study how the outer solar system developed. The asteroid belt between Mars and Jupiter contains many rocky leftovers from solar system formation. Rather than one failed planet shattered into pieces, it is better understood as a region where planetary building blocks remained as smaller bodies. Jupiter's gravity played an important role in preventing them from merging into a single large planet. Small bodies like asteroids and comets act as time capsules from the early solar system. Because many of them have changed less than larger worlds with active geology or thick atmospheres, they preserve older material and older clues. By studying them, scientists learn not only about those bodies themselves, but also about the deeper origins of planets and moons. Mercury is the smallest planet in the solar system, which gives it a very different character from the giant outer worlds. Even though it is small, it is still a complete planet with its own core, crust, magnetic field, and long history. Its size makes it feel closer to the scale of a moon than a giant world. Yet it still holds an important place in the architecture of the inner solar system. Mercury is also the nearest planet to the Sun, and that location shapes nearly everything about it. Because it circles so close to our star, it experiences intense sunlight, strong solar influence, and a sky environment very different from Earth's. Its place at the inner edge of the planetary family makes it one of the most extreme worlds among the rocky planets. Mercury is only slightly larger than Earth's moon, which often surprises people because planets are usually imagined as much larger than moons. In reality, Mercury and the Moon are not dramatically different in size, though they formed in very different ways and have very different roles in the solar system. That comparison helps make Mercury feel more real, because it shows that a planet does not have to be enormous to count as a full world. Mercury races around the Sun in just 88 Earth days, making it the fastest planet in the solar system. Its year is so short because it travels along a tight orbit close to the Sun, where gravity is stronger and orbital speeds are higher. In simple terms, Mercury has a smaller track to follow and must move very quickly to stay in that path. Even though Mercury is the closest planet to the Sun, it is not the hottest planet. That detail sounds backward at first, but it makes sense when atmosphere is taken into account. Mercury has almost no substantial atmosphere to trap heat, while Venus holds heat extremely well under its dense blanket of gases, making Venus much hotter overall. Mercury is the second densest planet after Earth, which tells scientists something important about what it is made of inside. High density usually means a world contains a large amount of metal and rock, packed into a relatively small volume. So although Mercury is small, it is built from very heavy material, especially deep within its interior. Mercury has an enormous metallic core that extends to about 85% of the planet's radius. This is an unusually large core compared with the size of the whole planet, and it is one reason Mercury is so dense. Its interior structure suggests that metal dominates a huge share of its body, giving the planet a very compact and iron-rich nature. Evidence suggests that part of Mercury's core is still molten or liquid, which means the planet is not completely frozen solid inside. That matters because a partially liquid core can help explain how Mercury maintains a magnetic field. Even on a small world so close to the Sun, the deep interior can still remain active in ways that continue to shape the planet today. Mercury's outer shell is relatively thin compared with the size of the planet. In other words, beneath a thinner rocky outer layer, lies a very large core that dominates the structure of the world. This makes Mercury different from many other planets and helps astronomers understand that rocky planets can form with very different internal balances. Mercury is hard to observe from Earth because the sun's glare usually overwhelms it. Since it never appears very far from the sun in our sky, it is often lost in bright twilight or buried in daylight. That means one of the nearest planets can actually be one of the trickiest for casual observers to spot clearly. Mercury transits across the face of the sun only about 13 times per century. During a transit, the planet appears as a tiny dark dot moving across the sun's bright disk. These events are uncommon and require careful observation, which makes them special opportunities to watch orbital motion in a direct and elegant way. Mariner 10 was the first spacecraft to visit Mercury, marking the beginning of close-up exploration of this difficult inner planet. Before spacecraft arrived, Mercury was much more mysterious because observing it from Earth is so challenging. Mariner 10 helped turn Mercury from a distant, glare-hidden point of light into a place scientists could start to study in detail. Messenger became the first spacecraft to orbit Mercury, which allowed a much deeper and longer investigation of the planet. Orbiting meant it could map the surface, study the magnetic field, examine the composition, and build a far more complete picture than a brief flyby ever could. It changed Mercury from a partially known world into one of the best-studied rocky planets beyond Earth. A joint ESA-JAXA mission launched in 2018 to continue Mercury exploration, showing that this small planet still has many unanswered questions. Scientists remain interested in its strange interior, unusual density, magnetic behavior, and history of formation. The fact that Mercury continues to attract major missions shows that even the smallest planet can teach large lessons about how planets work. Venus is the second planet from the Sun, facing it just beyond Mercury in the inner solar system. Because of that position, it receives a great deal of solar energy, though its true character depends even more on its atmosphere than on distance alone. It is one of Earth's nearest neighbors, but in conditions it is far more hostile than our own world. Venus is Earth's closest planetary neighbor, which makes it especially important in planetary science. A nearby world is easier to study in detail than more distant planets, and Venus offers scientists a powerful comparison case. It helps show how two similar-sized rocky planets can end up with very different climates, surfaces, and histories. Venus is often called Earth's twin because of its broad similarity in size. At first glance, that makes it sound like it might be a second version of our world. But when scientists look closer, the differences become dramatic, which is exactly why the comparison matters so much. Similar size does not guarantee similar outcomes in planetary evolution. Venus is the hottest planet in the solar system, even hotter overall than Mercury. That extreme heat comes from its thick atmosphere, which traps energy very effectively through a runaway greenhouse effect. So Venus is a powerful reminder that atmosphere can matter just as much as distance from the Sun when it comes to a planet's temperature. The surface of Venus is hot enough to melt lead, which gives a vivid sense of just how severe its environment is. This is not merely a hot desert in the ordinary sense, but a world where the ground-level conditions are intense enough to affect metals that stay solid in many human-made settings. It is one of the clearest examples of a truly hostile planetary surface. Venus is wrapped in thick clouds that hide its surface from ordinary view. When people look at Venus in visible light, they are not seeing the ground, but the upper layers of its atmosphere. This means that for a long time, the planet's actual surface remained hidden, and scientists had to use radar and spacecraft to uncover what lay below those bright clouds. Venus has a toxic atmosphere and an extremely hostile surface environment. Its air is dominated by carbon dioxide. The pressure at the surface is crushing, and the temperature is intensely high. Together, those conditions create a world that is rocky like Earth in its basic type, yet profoundly unfriendly to anything like human life or human exploration, without heavy protection. Venus was the first planet ever visited by a spacecraft from Earth, which gives it an important place in the history of space exploration. Reaching another planet was a major step in human scientific achievement. It marked the beginning of a new era, when planets stopped being only telescopic objects and started becoming destinations for direct study. Mariner 2 flew past Venus on December 14, 1962, becoming a landmark mission in planetary science. That flyby confirmed that interplanetary exploration was truly possible and provided early direct measurements of Venus. It helped open the path for decades of later missions to planets, moons, and smaller bodies throughout the solar system. Dozens of spacecraft have been sent toward Venus, though not all succeeded. This tells us two things at once. Venus has been a major scientific target, and it is also a difficult place to study. Missions to Venus have challenged engineers with heat, pressure, and harsh atmospheric conditions, but the scientific value of the planet has kept drawing researchers back. NASA has planned new Venus missions called Veritas and Da Vinci, showing that interest in Venus remains strong. Scientists still want better answers about its surface, atmosphere, history, and why it turned into such an extreme world. In many ways, Venus may help reveal what can happen when a rocky planet follows a climate path very different from Earth's. Mars is the fourth planet from the Sun and sits just beyond Earth in the solar system's inner family of rocky worlds. Its position places it in a colder region than Earth, yet still close enough that it has become one of the main focuses of robotic exploration. Because it is a nearby terrestrial planet, Mars feels both distant and strangely familiar. Mars is a cold desert world with a very thin atmosphere. That means it has a rocky surface and dry landscapes, but with far less air above it than Earth has. The thin atmosphere affects temperature, weather, and the way the surface changes over time, creating a planet that can look dramatic and open, yet remains harsh and difficult for human survival. Mars has seasons, which makes it feel more Earth-like than some other planets. Those seasons happen because Mars is tilted on its axis, so different hemispheres receive different amounts of sunlight during its year. Even though Mars is much colder than Earth, the rhythm of seasonal change still shapes its atmosphere, polar regions, and surface patterns. Mars has polar ice caps, adding another familiar feature to an otherwise alien world. These caps grow and shrink with the seasons, reflecting changes in temperature and atmospheric behavior. Their presence also matters scientifically because ice preserves clues about climate history and the movement of water and carbon dioxide on the planet. Mars preserves extinct volcanoes, which tells us the planet once had major internal activity. Some of these volcanic structures are enormous, showing that Mars was capable of powerful eruptions and long geological development in its past. The fact that these volcanoes remain so well preserved also reflects how slowly the Martian surface changes compared with Earth's more active environment. Mars also preserves giant canyons, including some of the largest known anywhere in the solar system. These features show that Mars has undergone dramatic shaping processes over time, from tectonic stretching to erosion and collapse. A canyon on Mars is not simply a crack in the ground. It can be a vast regional feature that speaks to the planet's deep geological history. Mars still has weather despite its thin atmosphere. Its air may be much less dense than Earth's, but it can still move dust, form clouds, and create seasonal changes. This is important because it shows that even a relatively sparse atmosphere can remain active enough to shape a planet's appearance and environment. NASA describes Mars as the only planet known to be inhabited entirely by robots. That phrase is playful, but it captures something real and important. Mars is the world where human-built machines now travel, drill, analyze, photograph, and transmit information back across space, acting as our distant explorers on the ground and in orbit. NASA currently operates multiple spacecraft at Mars, including orbiters and rovers. This allows scientists to study the planet from several angles at once. Orbiters can map the whole world and examine the atmosphere from above, while rovers can investigate rocks, soil, and local conditions directly on the surface. Mars has two moons, Phobos and Deimos, and both are quite different from Earth's large round moon. They are smaller, darker, and more irregular in shape, giving the Martian system a more rugged appearance. Their existence adds another layer to Mars as a planetary system, rather than just a single isolated world. Phobos and Deimos are thought either to be captured asteroids or debris from the early solar system. This means their origin is still part of an important scientific puzzle. Whether they were caught by Mars's gravity or formed from material linked to ancient impacts or early system processes, they carry clues about how planetary companions can arise. Both Martian moons are dark, lumpy, heavily cratered, and covered with dust and loose rocks. They do not look like smooth, bright spheres. Instead, they resemble battered fragments shaped by impacts and long exposure to space. Their rough appearance helps make them feel like ancient leftovers from a rougher, earlier solar system. Phobos and Deimos always keep the same face turned toward Mars. This is called tidal locking, and it means each moon rotates in step with its orbit. So just as Earth's moon always shows us the same side, the Martian moons maintain one constant hemisphere facing their planet as they circle it. Future astronauts on Mars will have to cope with freezing temperatures, radiation, fine dust, and corrosive salts. In other words, Mars is not simply empty and cold. It presents a whole set of environmental challenges that affect equipment, health, shelter, and long-term survival. Studying these hazards now is part of preparing for any realistic future human mission. Mars exploration today mixes the search for ancient life with practical testing for future human missions. Scientists want to know whether Mars ever had environments suitable for life, especially microbial life long ago. But they also use missions to understand landing systems, resources, weather, terrain, and risks for future crews. So Mars is both a scientific target and a training ground for deeper exploration. Earth is the third planet from the Sun, positioned in the inner solar system between Venus and Mars. That location helps define its temperature range, the behavior of its atmosphere, and the conditions that support liquid water at the surface. Earth's place is not the whole story of habitability, but it is an important part of why our world developed as it did. Earth is one of the 4 terrestrial planets, meaning it belongs to the rocky inner group that also includes Mercury, Venus, and Mars. These planets are built mostly from rock and metal, rather than thick layers of gas. Even within that shared category, though, Earth stands out because of its oceans, climate balance, and rich biosphere. NASA Glossary describes Earth as the only planet known to have large quantities of water. That is a major reason Earth is so different from the other rocky planets we know well. Water shapes climate, surface change, chemistry, and life itself, making it one of the defining features of our planet. Earth's atmosphere supports a huge variety of life forms, which makes it far more than just a layer of air. It regulates temperature, moves water through the climate system, supplies essential gases for living things, and protects the surface from some harmful radiation. In many ways, Earth's atmosphere is part of what makes the planet a living world. Earth has one natural satellite, the Moon, and that single companion has had a deep influence on our planet. The Moon affects tides, contributes to the stability of Earth's axial tilt, and has shaped human culture and science for thousands of years. A single moon may sound simple, but its presence has had very large consequences. Earth's moon is about 3.7 times smaller than Earth, making it relatively large compared with its planet when judged against many other moon-planet pairings. This is one reason the Earth-Moon system is especially interesting. The Moon is not nearly as big as Earth, of course, but it is still large enough to have major visible and physical effects. The Moon's average distance from Earth is about 400 kilometers. That is far enough to make travel a major challenge, yet close enough that the Moon still feels visually present in our everyday sky. It is close in cosmic terms, but still distant enough to remind us that even our nearest world beyond Earth lies across a meaningful stretch of space. The Moon is generally a solid world rather than a gaseous one, like most planetary moons. This means it has a rocky body with a surface, crust, and internal structure more comparable to a planet than to a gas giant. It is a proper world with ground, dust, mountains, basins, and a real geological story of its own. Water exists on both sunlit and permanently shadowed parts of the Moon. That discovery changed older ideas that treated the Moon as entirely dry. Lunar water may appear in different forms and concentrations, but its presence matters greatly because it affects how scientists understand the Moon's history and how future explorers might use local resources. Scientists think lunar water has multiple sources, including comet impacts, micrometeorites, and solar wind interactions with lunar dust. This means the Moon's water story is not simple or tied to only one event. Instead, it may reflect many processes acting over long periods, gradually supplying or creating water-related material across different environments on the lunar surface. The Moon can produce total solar eclipses because the Sun is about 400 times wider than the Moon, but it is also about 400 times farther away from Earth. That unusual balance makes the two bodies appear almost the same size in our sky, even though they are actually enormously different in physical size. Because of that coincidence, the Moon can sometimes cover the Sun almost perfectly, creating one of the most dramatic sights in astronomy. That near match in apparent size is one of the most striking coincidences in skywatching. It is not something that has to happen everywhere in the universe, and it does not even remain exactly the same forever across long cosmic timescales. But for human observers on Earth, it creates a rare and beautiful situation where a relatively small nearby object can briefly hide a much larger distant star. 4 nations had successfully landed on the Moon by January 2024, showing that lunar exploration is no longer part of only one country's history. The Moon has become a place of growing international effort, with different nations building their own engineering paths, scientific goals, and landing systems. This broadens the story of lunar exploration and makes the Moon feel less like a past achievement and more like an active frontier. The Apollo missions placed 12 American astronauts on the lunar surface between 1969 and 1972. Those landings remain some of the most famous events in the history of science and engineering because they turned the Moon from a distant object of observation into a place humans had physically walked on. The missions also returned samples and measurements that still matter to researchers today. The Moon is one of the easiest space objects to follow with the naked eye because of its brightness and regular phases. You do not need special instruments to notice its changing shape, its rising and setting, or its movement across the month. That makes the Moon one of the most familiar astronomical objects, even though it is also a real world with a long and complex geological history. Jupiter is the 5th planet from the Sun, placing it at the boundary between the smaller, rocky inner planets and the much larger giant worlds beyond. Its position helped shape the architecture of the solar system, because a planet with Jupiter's mass influences the motions of many nearby bodies. It is not just another planet in line, but one of the main gravitational powers in the solar system. Jupiter is the largest planet in the solar system, and its scale changes how people understand planets once they compare it with Earth. It is so much bigger than the terrestrial worlds that it belongs to a very different kind of planetary experience. When scientists study Jupiter, they are not looking at a rocky surface world made a bit larger, but at a giant atmospheric world with immense depth and energy. If Jupiter were hollow, about 1,000 Earths could fit inside it. That comparison helps translate its vast size into something easier to imagine. Instead of just hearing that Jupiter is large, you can picture an entire 1,000 Earth-sized worlds packed into the space it would occupy, which gives a much more direct sense of its enormous scale. Jupiter has the shortest day of any planet in the solar system, spinning once in about 9.9 hours. That is especially striking because such a huge planet rotates so quickly. This rapid spin affects Jupiter's shape, atmospheric behavior, and overall dynamics, helping create the banded appearance and powerful circulation patterns that make the planet so distinctive. Jupiter's colorful bands are made of cold, windy clouds of ammonia and water. These clouds do not sit still like painted stripes. They are part of a deep, active atmosphere shaped by chemistry, temperature differences, and fast-moving winds. What looks calm from a distance is actually a complex and changing planetary weather system. The darker stripes on Jupiter are called belts. These regions are part of the planet's layered atmospheric structure and are associated with certain types of flow and cloud behavior. Even something as visually simple as a dark band on Jupiter reflects a deep and active system of gases moving over a giant spinning world. The lighter bands on Jupiter are called zones. They alternate with the darker belts and help give Jupiter its famous striped appearance. These lighter regions are not just decorations of color, but signs of organized atmospheric motion, showing that Jupiter's cloud tops are shaped by large-scale patterns acting across the planet. Jupiter's belts and zones flow east and west in opposite directions. This means neighboring atmospheric bands can move against one another, creating boundaries of strong wind shear and constant interaction. The result is a planet whose visible surface is really a dynamic atmospheric map, full of motion, turbulence, and layered circulation. The Great Red Spot is a giant storm larger than Earth. That alone makes it extraordinary, because storms on Earth are already powerful and destructive. Yet on Jupiter, the scale becomes planetary. The Great Red Spot is not just a weather event in the ordinary sense. It is a long-lived atmospheric system so large that it changes how we imagine what a storm can be. The Great Red Spot has persisted for hundreds of years, which makes it even more unusual. On Earth, storms come and go on much shorter timescales, but Jupiter's atmosphere can sustain giant structures for far longer. This tells scientists that the energy, scale, and fluid behavior of Jupiter's atmosphere are very different from what we are used to on our own planet. Jupiter is also described by NASA as the oldest planet in the solar system. That means it likely formed very early, during the solar system's youth, while the raw building processes of planets were still underway. Because of its early formation and huge mass, Jupiter may have strongly influenced the later arrangement of many other bodies in the solar system. Jupiter has 95 officially recognized moons, giving it one of the richest moon systems in the solar system. These moons range from large, planet-like worlds to small, irregular bodies, making Jupiter feel less like a single planet and more like a system of many worlds gathered around one giant center of gravity. Jupiter's moon system also includes thousands of much smaller objects sharing its orbital environment. So the Jovian system is not made only of the officially named large moons. It also includes swarms of small bodies and companions that show how active and crowded a giant planet's gravitational domain can become. Jupiter's 4 large Galilean moons were the first moons discovered beyond Earth. Their discovery was historically important because it showed that not everything in the heavens circles Earth. In that sense, these moons helped change humanity's understanding of the universe, not just by existing, but by what their existence proved. Ganymede, one of the Galilean moons, is the largest moon in the solar system. It is bigger than the planet Mercury, which reminds us again that moons can be remarkably large and complex worlds. Ganymede is not simply a small companion of Jupiter, but a major body in its own right. Europa is an ocean moon that has become one of the prime targets in the search for habitability. Scientists are deeply interested in it because evidence suggests it may hide a vast ocean beneath its icy outer shell. A moon far from the Sun may therefore contain one of the most promising environments for studying whether life-friendly conditions can exist beyond Earth. Io is famous for extreme volcanism, making it one of the most geologically active bodies in the entire solar system. Instead of being a frozen or quiet moon, it is a world of constant internal stress and volcanic activity. Its surface is repeatedly reshaped by eruptions, showing how powerful gravity-driven heating can be inside a moon. Callisto is another large Galilean moon, but it is distinct from volcanic Io and ocean-bearing Europa. This is part of what makes Jupiter's moon system so remarkable. Its major moons are not copies of one another. Each one has a different personality, structure, and history, creating a diverse family of worlds around one planet. Many of Jupiter's outer moons have highly elliptical orbits. That means their paths around the planet are stretched rather than nearly circular, which often points to a more complicated dynamical history. Such orbits suggest that some of these moons may have been captured or otherwise shaped by gravitational interactions over time. Many of those outer moons also orbit backward relative to Jupiter's spin. This backward motion, called retrograde orbit, is another clue that these moons are not simple products of the same formation process as the major regular moons. Their unusual motion makes them feel more like collected bodies than neatly formed companions. Europa goes around Jupiter once every 3.5 days, which is a very quick orbit for a world of such interest and complexity. Because it is relatively close to Jupiter, it feels strong gravitational effects from the giant planet. Those effects matter greatly because they help shape Europa's internal heating and long-term behavior. Europa is gravitationally locked, so the same hemisphere always faces Jupiter. This is similar to how Earth's moon always shows us the same face. Tidal locking is a natural outcome of long gravitational interaction, and it means Europa's relationship with Jupiter is steady and structured, with one side constantly turned toward its planet. Io, Europa, and Ganymede participate in an orbital resonance. In simple terms, their orbital periods are linked in a repeating mathematical pattern rather than behaving as completely independent motions. This kind of resonance is one of the elegant ways gravity organizes a planetary system over long periods. In that resonance, every time Ganymede orbits once, Europa orbits twice. This ratio is not just a curiosity. It means their motions are tied together in a stable repeating rhythm, and that rhythm helps maintain gravitational effects that influence their interiors and orbital shapes. In the same pattern, Io orbits 4 times for every 1 orbit of Ganymede. So across these 3 moons, the resonance forms a repeating chain of motion. That chain helps keep gravitational stresses active, and those stresses are part of why moons like Io and Europa are so scientifically fascinating. Saturn is the 6th planet from the Sun and one of the most recognizable worlds in astronomy. Even people with little background in planetary science usually know it as the ringed planet. But beyond that famous appearance, Saturn is also a huge and complex system with many moons, deep atmospheric layers, and long-term seasonal changes. Saturn is the second largest planet in the solar system, smaller than Jupiter but still vastly larger than Earth. Its size places it among the giant planets, where conditions are dominated by thick atmospheres and powerful gravity, rather than solid ground one could stand on in the ordinary sense. Saturn is made mostly of hydrogen and helium, the same light elements that dominate the Sun and much of the giant planet family. This composition tells us that Saturn is not a rocky world enlarged to giant scale. It is a very different kind of object, with deep layers of gas and fluid-like material under changing pressure conditions. Saturn is famous for its bright ring system, which makes it one of the most visually striking planets in the sky. The rings look smooth and solid from far away, but they are actually made of countless particles orbiting together. Their brightness and structure make Saturn feel almost unreal when first seen through a telescope. Saturn is the farthest planet that people can usually see with the unaided eye. That means a human observer under dark skies can sometimes detect, without a telescope, a world nearly 1.5 billion kilometers from the Sun. It is a quiet reminder of how far human vision can reach when looking into the night sky. A day on Saturn lasts only about 10.7 hours, showing that Saturn, like Jupiter, spins very quickly for such a large planet. Rapid rotation affects the planet's shape and atmospheric behavior, helping create broad patterns in the clouds and making Saturn slightly flattened at the poles. Saturn needs about 29.4 Earth years to orbit the Sun once. That means its seasons unfold very slowly compared with those on Earth. A child could grow into adulthood before Saturn completed one trip around the Sun, which helps show how different planetary timescales become in the outer solar system. Saturn's axial tilt is about 26.73 degrees, so it experiences seasons much like Earth does in a broad physical sense. Different hemispheres receive different amounts of sunlight over the course of its long year. Because Saturn's year is so long, though, each season lasts for many Earth years. Saturn currently has 274 confirmed moons, more than any other planet in the solar system. This huge number turns Saturn into a system of many worlds rather than simply a single planet with a decorative ring. Its moons vary enormously in size, shape, and behavior, making the Saturn system one of the richest destinations in planetary science. In March 2025 alone, astronomers confirmed 128 additional small moons around Saturn. This shows how active discovery still is, even in our own solar system. We often imagine the solar system as already fully counted and understood, yet modern observations continue to reveal new members in the planetary families around giant worlds. Saturn's larger moons tend to be spherical, but many smaller moons are oddly shaped. Gravity is strong enough in larger moons to pull them into rounder forms, while smaller ones can remain irregular, lumpy, or stretched. So the shapes of Saturn's moons tell a story about size, gravity, and structural history. NASA compares some small Saturnian moons to potatoes, meatballs, sponges, and dirty ice balls. Those comparisons are informal, but they help make the shapes easier to imagine. These are not polished, perfect spheres. They are often rough, irregular objects that show how messy and varied natural bodies can be. Titan is Saturn's largest moon and one of the most remarkable moons in the solar system. It is not just notable because of its size, but because it has an atmosphere, weather, and surface features that make it feel like a world with its own environmental systems, rather than merely a frozen satellite. Titan is the second largest moon in the solar system, after Ganymede. That puts it in a category of truly major moons, large enough to matter not only as companions of planets, but as worlds with deep scientific importance of their own. It is one of the places that most strongly expands the meaning of what a moon can be. Titan is larger than the planet Mercury, which surprises many people because moons are usually imagined as much smaller than planets. But classification depends on what an object orbits, not just on size. Titan remains a moon because it circles Saturn, even though in sheer scale it surpasses one of the solar system's official planets. Titan has a dense atmosphere made mainly of nitrogen and methane. That alone sets it apart from most moons, which have little or no substantial atmosphere. A thick atmosphere changes everything, from how the surface interacts with sunlight to how weather works and how scientists think about chemistry and possible prebiotic processes. Titan has huge liquid methane lakes, unique in the solar system. On Earth, lakes are made of water, but Titan is so cold that methane can play a similar role there. This means Titan has a strangely familiar-looking landscape built from very unfamiliar materials, making it one of the most alien and yet recognizable worlds we know. Ultraviolet light helps drive Titan's rich atmospheric chemistry by transforming molecules into hydrocarbons. In simple terms, sunlight helps trigger chemical reactions in the upper atmosphere, building more complex compounds over time. This is one reason Titan fascinates scientists. It is a natural laboratory where chemistry, atmosphere, and surface processes interact in unusual ways. Enceladus is one of Saturn's most geologically active moons, which is remarkable because it is much smaller than giant worlds like Titan. Despite its modest size, it shows signs of strong internal activity, proving again that a moon does not have to be huge to be dynamic. Small worlds can still be active, surprising, and deeply important. Enceladus has geysers powerful enough to affect Saturn's magnetic field measurements. That means its activity is not just a local surface event. Material from this moon is energetic and abundant enough to interact with the environment of the larger Saturn system itself, linking a small icy moon to planet-scale observations. Those geysers made it difficult to determine Saturn's day length using standard magnetic field methods. In many cases, scientists estimate a giant planet's rotation by studying patterns linked to its magnetic field. But Enceladus was active enough to interfere with that process, which means a small moon was able to complicate measurements of a giant planet. That is a beautiful example of how connected planetary systems can be, where even a moon can influence how we understand its much larger parent world. Mimas bears a crater so large that the impact nearly tore the moon apart. This tells us that small worlds can survive astonishingly violent collisions and still remain intact. The crater is not just a scar on the surface. It is evidence of a dramatic event in the moon's history, one so powerful that it came close to destroying the entire body. 4 robotic spacecraft have visited Saturn, which shows how important this planet has been in space exploration. Saturn is not only visually beautiful because of its rings, but scientifically rich because of its atmosphere, moons, and surrounding environment. Each visiting mission added another layer of understanding, helping turn Saturn from a distant ringed light into a deeply studied system. Cassini's arrival in orbit in 2004 transformed our understanding of the Saturn system. Orbiting Saturn allowed scientists to watch the planet and its moons over time, instead of just passing by once. That meant they could observe seasonal changes, study the rings in detail, and build a much fuller picture of moons like Titan and Enceladus. Cassini did not simply add information. It changed the entire scale of what we knew. Uranus is the 7th planet from the Sun, placing it deep in the outer solar system beyond Saturn. It belongs to the family of giant planets, yet it has a personality very different from Jupiter and Saturn. Its distance, color, tilt, and quieter appearance make it one of the strangest major planets in our system. Uranus has the 3rd largest diameter of any planet in the solar system. Only Jupiter and Saturn are wider, which means Uranus is still an enormous world, even though it often receives less attention than the larger gas giants. Its size reminds us that even the more distant planets are not minor background objects, but massive worlds with substantial systems of their own. Uranus is about 4 times wider than Earth. That is a useful comparison because it helps bring its scale into everyday understanding. Earth feels large to us because it is our whole world, but Uranus stretches far beyond that familiar size, making it a giant planet in a very real physical sense. Uranus appears to rotate on its side, which is one of the most unusual traits of any planet in the solar system. Instead of spinning in a more upright way, it seems tipped over so extremely that its orientation looks almost sideways. This makes the planet feel less like a standard globe in space and more like something rolling around the sun in an unusual posture. Its extreme tilt is close to 90 degrees relative to the plane of its orbit. That means Uranus experiences sunlight in a very unusual way over the course of its year. Rather than having ordinary seasons like Earth, it goes through extreme lighting conditions, with parts of the planet facing long stretches of sunlight or darkness unlike anything on our world. Uranus is very cold and windy, making it a harsh environment even by outer planet standards. The great distance from the Sun means it receives very little solar energy, yet its atmosphere is still active enough to support wind and changing conditions. So Uranus is not a frozen, motionless place. It is cold, but still dynamic. Uranus has faint rings, which many people do not realize because Saturn's rings are so much more famous. These rings are less bright and less visually obvious, but they show that ring systems are not unique to a single planet. Even a colder and more distant giant like Uranus can carry a structured collection of orbiting debris around itself. Uranus has more than 24 moons, turning it into a full planetary system rather than just a single isolated world. These moons add richness to the Uranian system and show that even planets far from the Sun can gather and hold many companions. Each moon also offers its own clues about formation, orbital history, and planetary evolution. NASA lists 28 known moons for Uranus. That count helps give a concrete sense of the complexity of the system. Uranus is not simply a distant blue-green planet drifting alone. It is surrounded by many smaller worlds, each moving under the planet's gravity in a system with its own internal variety. The 5 major Uranian moons are Miranda, Ariel, Umbriel, Titania, and Oberon. These names represent the largest and most studied companions of Uranus. Together they form the central moon family of the planet, giving astronomers several significant worlds to compare rather than just 1 or 2 isolated objects. Oberon and Titania are the largest moons of Uranus. Their size makes them especially important for understanding the system as a whole, because larger moons often preserve more substantial geological and structural histories. They are not just orbiting rocks, but major bodies that help define what the Uranian system is like. Only 1 spacecraft has ever visited Uranus. That fact alone explains why the planet still feels relatively mysterious compared with Jupiter, Saturn, or Mars. Much of what we know comes from remote observations and 1 brief encounter, which means Uranus remains one of the great underexplored major worlds in the solar system. That spacecraft was Voyager 2. Its visit gave humanity its first and only close look at Uranus, making the mission historically very important. Without Voyager 2, our picture of the planet and its moons would be far more limited and abstract. Voyager 2 gathered much of what we know about Uranus during a flyby lasting only a few hours. That is extraordinary when you think about it. A planet so large and distant has been studied up close only during a short passing moment. Yet that brief window provided an enormous share of our direct knowledge. Neptune is the 8th and most distant planet in the solar system. It marks the outer edge of the major planets and represents a region where sunlight is weak, travel times are long, and conditions become increasingly unfamiliar. Neptune feels like a true frontier world, sitting at the far edge of the classical planetary lineup. Neptune is the first planet discovered through mathematics before direct observation confirmed it. This makes its discovery one of the most elegant moments in science. Astronomers noticed that Uranus was not moving quite as expected, and instead of giving up, they used those small irregularities to predict the existence and location of another planet. Neptune is dark, cold, and whipped by supersonic winds. That combination makes it one of the most severe weather worlds in the solar system. Even though it is far from the Sun and receives relatively little energy, its atmosphere is still capable of intense motion, which shows that planetary weather can be powerful even in deep cold. Neptune is more than 30 times farther from the Sun than Earth is. This enormous distance shapes everything about the planet, from its temperature to its brightness in our sky. It also helps explain why human understanding of Neptune developed slowly compared with the nearer planets. Sunlight at Neptune is roughly 900 times dimmer than sunlight on Earth. So even at midday there, the sun would not dominate the sky with the same strength we know here. This helps us picture Neptune not just as far away in distance, but as living under a much weaker version of solar light. Neptune cannot be seen with the naked eye. Unlike Saturn, which can just barely be spotted under the right conditions, Neptune remains beyond ordinary, unaided human vision. That means its existence and nature belong entirely to the age of telescopes, mathematics, and modern astronomy. Neptune completed its first full 165-year orbit since discovery in 2011. That fact gives a strong sense of just how slow the years are in the outer solar system. Since the planet was discovered in the 19th century, it took until the 21st century to finish a single Neptunian year. NASA currently lists 16 known moons for Neptune. That number makes Neptune a moon system as well as a planet, though not as crowded as Jupiter or Saturn. Each moon adds another piece to the story of how Neptune's outer system formed and evolved. Triton is Neptune's largest moon and the dominant member of the Neptunian moon family. It stands out not only because of its size, but because it is one of the most unusual large moons in the solar system. In many ways, learning about Neptune means learning about Triton as well. Triton was discovered just 17 days after Neptune itself was identified. This quick follow-up is remarkable because it shows how rapidly astronomers began uncovering the structure of the new planetary system. Almost as soon as Neptune entered scientific awareness, it was already becoming clear that it did not travel alone. Webb has captured images of 7 of Neptune's moons in a single portrait. That kind of image is scientifically useful, but it also changes the emotional feel of the system. Instead of imagining Neptune as one distant blue world, we can see it visually as a gathering of multiple bodies held together by gravity. Triton dominates that Webb portrait as a very bright point of light. This visual prominence reflects its major role within the Neptune system. It is not just one moon among many tiny companions, but a substantial world that stands out strongly, even in a broader planetary image. Pluto is a dwarf planet in the Kuiper Belt beyond Neptune. That places it in the cold outer region of the solar system, where many icy bodies orbit far from the Sun. Pluto is therefore both a specific world and part of a much larger population of distant objects that preserve clues about the early solar system. Pluto was reclassified from planet to dwarf planet in 2006 by the International Astronomical Union. This change was not a sign that Pluto became less real or less interesting. Instead, it reflected a refinement in how scientists sort and define bodies in the solar system as they learn more about the many objects beyond Neptune. Pluto is geologically complex. with mountains, valleys, plains, craters, and glaciers. That was a major surprise, because distant, small, icy worlds were once often imagined as simple and inactive. Pluto showed that even far from the Sun, a dwarf planet can preserve a rich and varied surface, shaped by real geological processes. One of Pluto's most famous features is the bright heart-shaped region seen by New Horizons. This feature quickly became iconic because it gave Pluto a distinctive visual identity in the public imagination. Scientifically, it also drew attention because it revealed that Pluto's surface contains large, organized regions with clear variation and structure. New Horizons became the first spacecraft to explore Pluto up close in 2015. That flyby transformed Pluto from a blurred, distant body into a real world with landscapes, textures, and history. It was one of the great moments of modern planetary exploration because it opened a door onto a region of the solar system that had never before been seen in detail. Ceres is the largest object in the asteroid belt between Mars and Jupiter. That means it holds a special place among the many rocky bodies in that region. It is not just another asteroid, but the dominant body of the belt, and large enough to be classified as a dwarf planet. Ceres is also the only dwarf planet located in the inner solar system. All the other officially recognized dwarf planets lie in much more distant regions, which makes Ceres unique. It is a dwarf planet much closer to the Sun and closer to Earth's neighborhood than Pluto, Eris, or the others. Ceres makes up about 25% of the asteroid belt's total mass. That is a striking amount for a single object to hold within such a broad region. Even though the asteroid belt contains many bodies, one world still accounts for a quarter of the belt's entire mass. Even so, Pluto is still about 14 times more massive than Ceres. This comparison helps show that not all dwarf planets are alike in scale. The category includes bodies with very different masses, structures, and positions in the solar system. NASA Dawn spacecraft explored Ceres directly, giving scientists a close look at the largest body in the asteroid belt. Missions like Dawn matter because they turn categories into places. Instead of only speaking about the asteroid belt in general, scientists could study one major world there as a real, detailed destination. Haumea is one of the fastest rotating large objects in the solar system. Fast rotation can strongly affect a body's shape and behavior, especially if the object is not extremely massive. Haumea's rapid spin makes it a particularly unusual dwarf planet, and a reminder that rotation can be just as important as size in shaping a world. Makemake is the second brightest object in the Kuiper belt. Brightness matters because it affects how easily astronomers can detect and study distant bodies. In such a remote region, standing out in brightness helps make an object especially important for observation and comparison. Eris is one of the largest known dwarf planets. It played a major role in the debates that led to Pluto's reclassification because its discovery helped show that Pluto was not a one-of-a-kind outer world. Eris expanded the known family of distant dwarf planets and forced astronomy to think more carefully about planetary definitions. Haumea is unusual not only because it is a dwarf planet, but also because rings have been found around it. This adds another layer of strangeness to an already unusual body. Rings had once seemed like the signature of giant planets, yet here they appear around a much smaller distant world. Chariklo, a much smaller body called a centaur, also has rings. That discovery widened scientific expectations even further. It showed that ring systems are not restricted to planets or even dwarf planets, but can also appear around comparatively small objects moving between the giant planets. The outer solar system includes many icy objects that preserve primitive materials from early times. These distant bodies matter because they often record ancient conditions more clearly than worlds that have been heavily reshaped by heat, weather, or strong geological activity. In that sense, the far outer solar system acts like a storage region for deep cosmic history. Arrokoth, visited by New Horizons in 2019, looked like a partially flattened snowman. Its shape made it instantly memorable, but the deeper importance was scientific. It gave researchers a close-up view of a very primitive small body and offered clues about how such objects formed and came together in the early solar system. NASA describes Arrokoth as the most distant and most primitive object ever explored by a spacecraft. That means it is both far away and scientifically valuable as a preserved relic of early planetary building. Exploring such an object is like opening a very old record book from the solar system's beginning. Asteroids are ancient leftovers from solar system formation. They are not failed curiosities with no broader meaning, but surviving building blocks from an earlier era. By studying them, scientists gain a clearer picture of the materials and processes that existed when the planets were first taking shape. Because of that, asteroids provide clues about how planets like Earth formed. They carry information about the raw ingredients of the early solar system and about the collisions and growth processes that eventually built larger worlds. In this way, small rocky bodies help explain the origin story of planets much bigger than themselves. Some asteroids may also have delivered complex molecules and possibly ingredients relevant to early life, to Earth. This idea matters because the early Earth was not developing in isolation. Material from space was falling here in the young solar system, and some of those incoming bodies may have carried carbon-rich compounds or water-related chemistry. So when scientists study asteroids, they are not only studying distant rocks. They are also asking whether pieces of space may have helped prepare the conditions that life later used here on Earth. Bennu is one asteroid that may contain carbon-bearing material and water-related compounds. That makes it especially valuable to scientists because carbon chemistry and water-related minerals are deeply connected to questions about the early solar system and the ingredients of habitable worlds. Bennu is not being studied only because it is nearby. It is being studied because it may preserve a record of ancient chemistry that larger, more changed worlds no longer keep so clearly. OSIRIS-REx became the first US mission to collect a sample from an asteroid. That was a major step in planetary science because it moved beyond photography and remote measurement into direct physical return. A sample return mission allows scientists to examine real material from an ancient body using precise laboratory tools on Earth. That creates a much deeper level of study than a spacecraft alone can provide from a distance. The mission returned material from Bennu to Earth on September 24, 2023. That return was the payoff for years of careful travel, mapping, sampling, and navigation across space. It also meant that pieces of an ancient asteroid were now available for direct study in Earth laboratories. Instead of only inferring Bennu's composition from instruments in orbit, scientists could now work with the material itself. After delivering the sample, the spacecraft continued on as OSIRIS-APEX toward asteroid Apophis. This shows how a mission can evolve rather than simply end after one success. Spacecraft are valuable tools, and when they still have capability left, scientists often find new uses for them. In this case, one mission transformed into another chapter of asteroid science, extending its life and purpose. Asteroid sample return allows scientists to study ancient solar system material in laboratories on Earth. That is important because Earth-based labs can do many kinds of detailed testing that are difficult or impossible to perform on a spacecraft. Researchers can measure tiny chemical traces, compare minerals carefully, and preserve samples for future tools not yet invented. In this way, one returned sample can support decades of science. Ryugu and Bennu are often compared because both are primitive near-Earth asteroids studied in great detail. Comparing two similar bodies helps scientists see what is shared and what differs across ancient asteroids. That, in turn, improves understanding of how such bodies formed, changed, and preserved material over time. A comparison like this makes asteroid science more than a one-object story. It becomes a broader study of early solar system diversity. Comets are icy bodies that also preserve early solar system material. While asteroids are often rockier, comets store large amounts of ice and volatile compounds, making them especially useful for studying the colder outer regions of solar system history. When a comet is examined closely, it can reveal chemistry and structure from a very ancient time. In that sense, comets are like frozen archives traveling through space. Rosetta discovered a kind of ultraviolet aurora at comet 67P/Churyumov-Gerasimenko. That was a surprising finding because auroras are usually associated in people's minds with planets and polar skies. A comet seems like a very different kind of object, much smaller and far less structured than a planet. Yet it still showed an auroral process, proving that energetic interactions in space can create familiar effects in unfamiliar places. That means auroral processes are not limited to planets with strong global magnetic fields. In simple terms, nature can create related phenomena under a wider variety of conditions than the basic textbook version might suggest. The universe often repeats physical principles in different settings, which is one reason astronomy keeps surprising people. What seems at first like a special effect of one kind of world can turn out to be part of a much larger pattern. The Sun emits a stream of charged particles known as the solar wind. This is not wind in the everyday Earth sense, because it is not moving air. Instead, it is a constant outflow of particles from the Sun, spreading through the solar system and interacting with planets, moons, magnetic fields, and interplanetary space. The solar wind is one of the main ways the Sun reaches outward and shapes its wider environment. The solar wind can reach speeds of up to about 900 kilometers per second in ESA's description. That is an extraordinary speed by any human standard. It helps explain why the solar wind is such an important force in the solar system, even though it is very thin. Fast-moving charged particles can still have powerful effects when spread across such immense distances and sustained over long periods. NASA describes the solar wind as much less dense than Earth's wind, but vastly faster, typically around 1 to 2 million miles per hour. This contrast is helpful because it reminds us that density is not the only thing that matters. Even though the solar wind is sparse, its speed and constant flow make it a major influence in space weather and planetary interactions. In space, something can be thin and still be very important. The solar wind consists of charged particles such as electrons and ionized atoms. Because these particles carry electric charge, they do not behave like ordinary neutral gas alone. They respond to magnetic fields and can shape plasma environments around planets and spacecraft. This is why heliophysics, the study of the Sun's influence, is so tied to both particle physics and magnetism. The solar wind and the Sun's magnetic field together create the heliosphere. You can think of the heliosphere as a vast bubble-like region where the Sun's outflow dominates the surrounding space. It is not a solid boundary, but a broad sphere of influence. Everything inside it exists in an environment shaped in important ways by our star. The heliosphere is the Sun's region of influence within interstellar space. That means our solar system is not just a collection of planets around the Sun, but also a larger magnetic and particle environment carried outward by solar activity. The heliosphere marks the area where the Sun still has the strongest direct control over local space conditions, before the wider galaxy takes over. Voyager 1 and Voyager 2 are the only spacecraft ever to operate outside the heliosphere. That makes them unique in the history of exploration. These probes are not simply far from Earth. They've gone beyond the Sun's main surrounding bubble and into interstellar space, becoming humanity's first machines to study that transition directly. Voyager 1 crossed the interstellar boundary in 2012. This was a landmark moment because it marked the first time a human-made object was confirmed to move beyond the heliosphere into the surrounding galactic medium. It did not mean Voyager had left the solar system in every possible sense, but it had entered a new environment where the Sun's influence was no longer dominant in the same way. Voyager 2 crossed that boundary in 2018. Having both spacecraft make the crossing gave scientists a second opportunity to compare conditions and understand the edge of the heliosphere more clearly. Two probes in different directions provide much more insight than one alone, because they show that the Sun's outer boundary is not a perfectly simple shell. The Voyager spacecraft were launched in 1977 and are still producing science after more than 4 decades. That longevity is one of the most impressive achievements in space exploration. Few technologies are expected to remain useful for so long, especially after traveling through deep space for decades. The Voyagers are a reminder that carefully built machines can continue extending human knowledge long after their launch era has passed into history. In October 2024, Voyager 1 temporarily stopped communicating with Earth. For a mission so old and so distant, any interruption naturally raises concern. Communication across such immense distances already takes patience, and a problem with a spacecraft this old can seem final. Yet the incident also showed how much care and skill mission teams still bring to these historic probes. Mission teams restored communication and kept Voyager 1 operating. That recovery was remarkable because it involved working with aging technology across interstellar-scale distances. It shows that these spacecraft are not simply relics drifting unattended. They remain active scientific tools supported by people on Earth who continue to solve problems and protect their long lives in space. Auroras happen when energetic particles from the Sun interact with Earth's magnetic field and atmosphere. The process begins in space, but the visible result appears in the sky above Earth as shifting curtains or glows of light. These displays are beautiful, but they are also physical evidence that our planet is linked to solar activity in a direct and ongoing way. Earth's magnetosphere acts like a shield that diverts much of the solar wind around the planet. It does not stop everything completely, but it provides strong protection by guiding many charged particles away from the atmosphere and surface. Without that magnetic shielding, Earth's environment would behave very differently, and life at the surface would face a harsher space environment. The solar wind stretches Earth's magnetic field into a long tail on the night side called the magnetotale. So Earth's magnetic field is not a perfect bubble. It is compressed on the sun-facing side and pulled out behind the planet like a long stream. This stretched structure is part of why space weather around Earth is dynamic rather than static. Magnetic reconnection helps power auroral displays. In simple terms, this process happens when magnetic field lines break and reconnect in ways that release energy and accelerate particles. Those particles can then move into Earth's upper atmosphere and contribute to auroras. It is a subtle but powerful process, showing how invisible magnetic structures can lead to visible beauty in the sky. Strong geomagnetic storms can push auroras to unusually low latitudes. Normally, auroras are more common closer to polar regions because of how Earth's magnetic field guides incoming particles. But during stronger storms, the disturbance becomes large enough that the glowing displays spread much farther from the poles, surprising people in places where they are rarely seen. In May 2024, an extreme geomagnetic storm made auroras visible in many regions where they are uncommon. This event helped many people experience directly that space weather is not just an abstract scientific topic. Solar activity can reshape the sky across broad parts of Earth, and remind us that our planet sits inside a changing solar environment, not apart from it. Space weather affects more than beauty in the sky. It also matters for spacecraft and human technology. Energetic particles and magnetic disturbances can interfere with satellites, communications, navigation systems, and power infrastructure. So heliophysics is not only about understanding the sun for curiosity's sake. It is also about protecting the technologies modern societies rely on. The same heliophysics processes that shape Earth's space environment also matter for Mars, Venus, and exoplanets. That is important because it means the sun's influence is part of a broader planetary science question. To understand whether a world can hold an atmosphere, protect a surface, or remain habitable, scientists often need to understand how solar or stellar activity interacts with it over long periods. Stars are giant balls of hot gas that shine for millions to billions of years. Their light comes from deep internal processes, and their lifetimes depend strongly on their mass. Some stars burn quickly and die relatively young, while others glow much more slowly and endure for enormous spans of time. A star is not just a bright dot, but a long-lived physical engine. Red dwarfs are the most common type of star in the Milky Way. That means the kind of star most people think of as typical, something like the Sun, is not actually the most common in our galaxy. Instead, the galaxy is filled mostly with smaller, cooler stars, making red dwarfs a major part of the true background population of the Milky Way. NASA Glossary says red dwarfs account for about 75% of the stars in our galaxy. This makes them not just common, but overwhelmingly important in the overall stellar population. If you could sample stars across the Milky Way, most of them would belong to this cooler, smaller class, rather than to bright sun-like stars. Red dwarfs can have masses as low as about 8% of the Sun's mass. That means they sit much lower on the scale of stellar mass, while still remaining true stars. This lower mass affects how they shine, how hot they are, and how long they live, making them very different from larger, brighter stars. A neutron star is one of the densest objects astronomers can observe directly. It forms when a massive star collapses after its life cycle ends, leaving behind an incredibly compact remnant. The result is a body so dense that ordinary human-scale intuition almost stops being useful. It is a star remnant pushed to an extreme physical state. NASA compares a typical neutron star to squeezing roughly 500,000 Earth masses into a sphere about 12 miles across. That comparison is so dramatic because it combines two scales that do not seem like they belong together. Enormous planetary mass is packed into something only about the size of a city, producing a density far beyond anything in normal life. That means a city-sized object can outweigh planets by astonishing amounts. When astronomy reaches these scales, words like big and small begin to lose their ordinary meaning. A neutron star is small in width compared with a planet, yet massive enough to overpower entire worlds in terms of gravitational significance. Neutron stars are often observed as pulsars. A pulsar is a neutron star that sends beams of radiation into space. And if those beams sweep past Earth as the star spins, astronomers detect regular pulses. This makes some neutron stars act almost like cosmic lighthouses, not because they're blinking on and off, but because their rotation carries the beam across our line of sight. Some neutron stars are found in X-ray binaries rather than as isolated pulsars. In those systems, the neutron star is paired with another star, and matter from the companion can fall toward the neutron star. That infilling matter heats up intensely and can produce powerful X-rays, making the system detectable in a very different way from a classic pulsar. Magnetars are neutron stars with extremely strong magnetic fields. Their magnetism is so intense that they represent one of the most extreme known forms of magnetic behavior in the universe. A magnetar is therefore not just a dense stellar remnant, but a highly specialized and violent one, where magnetic energy plays a dominant role. Soft gamma-ray repeaters are rare high-energy sources thought to be associated with magnetars. These sources release bursts of powerful radiation, linking them to some of the most energetic events observed in astrophysics. Their rarity and intensity make them especially important for understanding the extreme behavior possible in compact stellar remnants. Gamma-ray bursts, blazar jets, and supernova remnants are among the universe's most violent high-energy phenomena. These are not gentle background events. They involve enormous energies, extreme particles, and environments far beyond anything the solar system normally experiences. High-energy astronomy exists largely to study this more dangerous and dramatic side of the cosmos. Black holes are not empty holes, but extremely dense concentrations of matter packed into tiny regions. The phrase black hole can sound like a kind of cosmic opening or gap, but physically the object is better understood as matter collapsed into a very compact state. Its defining feature is not emptiness, but gravity so strong that escape becomes impossible past a certain boundary. The event horizon is the boundary beyond which not even light can escape a black hole. This is the line that makes a black hole truly black, because light itself cannot return once it passes inward. The event horizon is not an object you can stand on or see directly in a simple way, but it defines the region where escape ceases to be possible. The event horizon is not a hard surface like a planet's crust. That distinction matters because people naturally imagine boundaries as solid edges. But the event horizon is a gravitational boundary, not a material shell. It marks a change in what paths through space-time are still possible, which is a subtler and stranger idea than an ordinary surface. Black holes can reveal themselves through interactions with nearby matter. Since black holes do not shine directly in the normal sense, astronomers often detect them by what they do to their surroundings. Gas heating up, stars changing motion, or matter spiraling inward can all give away the presence of a black hole but would otherwise remain invisible. When a star gets too close to a black hole, tidal forces can tear it apart. This happens because gravity pulls much harder on the near side of the star than on the far side, stretching the star until it is disrupted. Such an event is one of the most dramatic examples of how black holes can shape and destroy nearby objects through pure gravity. Astronomers estimate that around 100 million black holes may roam the Milky Way. That is an extraordinary number, because it means black holes are not just rare exotic monsters at galaxy centers. Many may be scattered through our own galaxy as remnants of long-dead stars, most of them unseen unless something reveals them indirectly. Hubble provided the first direct evidence for a lone black hole drifting through interstellar space. This was especially important because many black holes are found through binary systems or active feeding environments. A lone black hole is much harder to detect, so finding evidence for one showed that even isolated invisible objects can sometimes be identified with careful observation. Some black holes can be surprisingly small by black hole standards, with reported examples near the boundary between neutron stars and black holes. This is scientifically valuable because it helps researchers understand where one class of compact object ends and another begins. The lower end of black hole size is not just a detail. It is part of a larger question about stellar death and collapse. Some black holes are so large that the word massive hardly seems enough. Supermassive black holes in galaxy centers can reach billions of times the mass of the Sun, which means the universe contains objects of almost unimaginable scale, hiding in what can look from far away like a calm galactic core. These giants help shape the regions around them and remind us that the largest structures in space are often tied to forces we cannot see directly. Black hole shadows can be compared to the scale of planetary orbits, and the shadow of Sagittarius A** spans about half the diameter of Mercury's orbit. That comparison is useful because it turns an abstract astronomical idea into something easier to picture. A shadow linked to a black hole is not just a tiny mark in space, but a structure large enough to be measured against the paths of planets, even though the black hole itself lies far across the galaxy. Binary supermassive black holes can form when galaxies merge. When two galaxies come together, their central black holes may eventually become a pair, moving in the same larger system. This means that even on the grandest scales, space is not static. Galaxies meet, combine, and reshape one another, and their central black holes can become part of that long cosmic dance. Quasars are among the bright beacons powered by matter falling towards supermassive black holes. They are not bright because the black hole itself glows in the usual way, but because material around it becomes extremely hot and energetic as it spirals inward. In some cases, a region around a black hole can outshine the combined starlight of the galaxy that holds it. Globular clusters are ancient star systems, and some very metal-poor examples have been found near the edge of the Milky Way. These clusters matter because they preserve very old stellar populations, giving astronomers a way to study conditions from earlier chapters of cosmic history. They are like densely packed time capsules made of stars. Ultra-faint dwarf galaxies can preserve evidence that their star formation was shut down long ago. These small and dim systems may look modest compared with giant galaxies, but they are deeply valuable because they preserve records of a much older universe. Their faintness is part of their importance, since it often means they changed less over time. Some dwarf galaxies can even contain supermassive black holes despite their small size. That is striking because people often assume only large galaxies would host such extreme central objects. But the universe does not always match human expectations, and even a relatively small galaxy can carry an enormous gravitational secret at its center. Space contains not just stars and planets, but also fossil systems that preserve early conditions from cosmic history. In other words, the universe holds ancient records in many different forms. Some objects shine brilliantly, while others quietly keep evidence of what conditions were like long ago. The Milky Way is only one galaxy among vast numbers in the universe. Our home galaxy feels huge when we think in terms of stars and planetary systems, yet on cosmic scales, it is only one member of a much larger population. This is one of the most humbling facts in astronomy, because it widens the idea of home into something much more expansive. Galaxy clusters can contain up to a few thousand galaxies bound together. So galaxies are not always isolated islands. On larger scales, they gather into enormous communities shaped by gravity, where many galaxies share a common environment across staggering distances. Hubble and Webb are complementary observatories rather than replacements for one another. Each telescope is designed for somewhat different strengths, and together they give astronomers a more complete picture of the universe. Science often advances not by one tool taking over entirely, but by multiple tools working side by side. Hubble and Webb together give astronomers a broader view of the universe than either could alone. One can reveal certain wavelengths and structures especially well, while the other is optimized for different kinds of light and different kinds of questions. When their observations are combined, the result is often richer than what a single telescope could provide. Webb is designed to look back more than 13.5 billion years toward the first galaxies. That means it is observing light from very early times in cosmic history, letting scientists study some of the universe's earliest large structures. Looking far away in astronomy also means looking far back in time. Webb uses a 5-layer sunshield to block heat from the Sun, Earth, and Moon. This is essential because the telescope is built to detect faint infrared signals, and it must stay very cold to do that well. The sunshield is not a minor attachment, but one of the key reasons Webb can perform its mission. NASA compares the effectiveness of Webb's sunshield to SPF 1,000,000. That comparison gives a vivid, everyday image for an extraordinary engineering system. It helps people imagine just how much heat must be booked so the telescope can remain sensitive to ancient faint warmth from the distant universe. Hubble has helped study the atmospheres of planets in the TRAPPIST-1 system. That matters because planets around other stars are no longer just points on a chart. With careful observation, astronomers can begin asking what kinds of gases surround them and how those distant worlds may differ from one another. TRAPPIST-1 is a Coulomb-class star, not a Sun-like G-class star. This means the system is built around a star quite different from our own, with different temperature, size, and behavior. Understanding the type of star is important because the nature of a star influences the environments of all the planets around it. Researchers have described the TRAPPIST-1 system as a 7-planet resonant chain. In simple terms, the planets follow linked orbital patterns, with their periods related in an orderly rhythm. Resonance like this shows that planetary systems can be arranged with surprising elegance rather than random spacing. Space-based observatories matter because many wavelengths of light never reach ground telescopes. Earth's atmosphere is wonderful for life, but it blocks large parts of the electromagnetic spectrum. To see the universe more fully, astronomers often have to place their observatories above the atmosphere altogether. X-ray astronomy opened a major new window on the universe by letting scientists study violent, hot, and compact objects. Many of the most energetic processes in space reveal themselves strongly in X-rays, not visible light. So opening that window changed astronomy from a science of mostly visible objects into something much broader and more powerful. Polarization measurements in X-rays can reveal the environments around pulsars, supernova remnants, and black holes. Polarization adds another layer of information beyond simple brightness and position. It helps scientists understand geometry, magnetic fields, and the physical conditions in some of the universe's most extreme places. Gaia's main goal has been to build the most precise 3D map of the Milky Way ever made. Mapping a galaxy from inside it is not easy, because we do not have the simple outside view we have of distant galaxies. Gaia helps solve that by measuring positions and motions with extraordinary precision. Gaia has surveyed about 1 billion stars for that map. That huge number shows the scale of modern astronomy, where missions can measure not just dozens or thousands of stars, but immense populations spread across the galaxy. This transforms the Milky Way from a rough idea into a structure that can be charted in much finer detail. Gaia is also expected to detect up to 10,000 planets beyond our solar system. So, while building a star map, the mission also contributes to exoplanet science. That overlap shows how modern observatories often serve many scientific purposes at once, rather than doing only one narrow job. The same mission also observes hundreds of thousands of asteroids and comets in our own solar system. This means Gaia helps with both galactic-scale astronomy and local solar system science. A single mission can therefore connect our understanding of nearby small bodies with our understanding of the wider Milky Way. The Vera C. Rubin Observatory is expected to generate an enormous flow of data for future discoveries. Astronomy is increasingly becoming a science not just of observation, but of massive information streams. Huge surveys can uncover changing objects, rare events, and unexpected patterns that smaller observing programs might miss. Modern astronomy is increasingly shaped by giant surveys that can uncover things no one specifically set out to find. That is one of the exciting features of large-scale observing projects. When the sky is studied broadly and repeatedly, discoveries often appear that were not part of the original plan. Pioneer 10 was the first spacecraft to visit the outer planets. That milestone expanded human exploration beyond the inner solar system and opened the path for deeper missions to the giant planets. It marked the beginning of direct study of a much larger and stranger part of our planetary neighborhood. Pioneer 10 made its closest approach to Jupiter on December 4, 1973. That moment gave humanity its first close look at the solar system's largest planet. A world that had long been studied through telescopes suddenly became a place that a spacecraft could pass beside and examine directly. After Jupiter, Pioneer 10 was sent onto a path that will eventually carry it out of the solar system. In that sense, the mission did not stop at one destination. It continued outward, becoming part of the long story of spacecraft that move from planetary exploration into deep space travel. Pioneer 10 last signal reached Earth in January 2003 from 7.6 billion miles away. That distance helps convey both the success of the mission and the vastness of space. Even a signal taking shape in human technology can travel across immense emptiness and still return a final whisper home. Voyager 2 remains the only spacecraft ever to visit both Uranus and Neptune. Because of that, it holds a unique place in the history of planetary exploration. Our direct knowledge of those two distant worlds depends heavily on one spacecraft's long outward journey. Spacecraft exploration has shown that even moons can be geologically active worlds rather than simple frozen rocks. This is one of the biggest changes in how people now think about the solar system. Moons are no longer seen as merely minor companions, but often as places with their own chemistry, internal heat, and surface change. In the Saturn system alone, one moon has methane lakes, another has major geysers, and another nearly shattered from a giant impact. This variety is extraordinary because it shows how different worlds can be even when they orbit the same planet. A single planetary system can contain landscapes and histories that feel almost unrelated to one another. In the Jupiter system, one large moon is volcanic, one likely hides an ocean, and another is the largest moon in the solar system. Again, a moon system turns out to be more like a collection of worlds than a set of repetitive objects. Around one giant planet, nature has built strikingly different environments. The solar system turns out to be less like a set of simple planets and more like a collection of many different planetary systems around one star. Each giant planet has moons, rings, small bodies, and its own internal complexity. The more closely scientists study it, the more the solar system feels layered and diverse. Space missions often continue producing science long after their original goals are finished. This happens because a healthy spacecraft can still observe, measure, and discover after its first objectives are complete. In space exploration, success often creates new possibilities rather than neat endings. Some missions even change identity midstream, as OSIRIS-REx did when it became OSIRIS-APEX. That kind of transition shows flexibility in science and engineering. A mission can finish one chapter, be redirected, and continue outward with a fresh purpose. Because of spaceflight, worlds once seen as mere points of light are now known as places with weather, chemistry, geology, and history. This may be one of the most profound changes in human understanding brought about by space exploration. Distant lights became actual landscapes and systems with stories of their own. Exploration has also shown that ordinary-seeming objects like asteroids and comets can hold clues about Earth's own origins. These small bodies may look less dramatic than planets or stars, but they preserve ancient material that helps explain how our world was built and what ingredients were present in the early solar system. Skywatching is not limited to stars. NASA highlights planets, the moon, meteor showers, comets, eclipses, satellites, and the space station as regular things people can follow in the sky. This makes astronomy feel close and personal because the sky is full of changing events, not just distant fixed lights. The International Space Station can be spotted from Earth without a telescope under the right conditions. That means a human-built outpost in orbit can become part of ordinary skywatching. Looking up and seeing it cross the sky links everyday life on Earth with ongoing human presence in space. Meteor showers happen when Earth passes through streams of debris left behind by comets. Tiny particles enter the atmosphere at high speed and briefly glow, creating the streaks people see as meteors. A meteor shower is therefore not random sparks in the sky, but Earth moving through a trail of cometary dust. The Leonids are caused by dust grains from Comet Tempel-Tuttle. This connects a named meteor shower to a specific comet, showing that sky events have clear physical origins. What looks like a fleeting display is really part of a larger orbital relationship between Earth and a returning comet. The Perseids peak in mid-August and are often called the best meteor shower of the year. Their popularity comes from a mix of reliability, brightness, and the pleasant time of year for many observers. They are a reminder that some of the most beautiful sky events are also regular and predictable. During a strong Perseid display, observers may see about 50 to 100 meteors per hour. That can turn the sky into a steady stream of brief flashes, giving people a direct sense of Earth moving through a dense region of cometary debris. Even though each meteor is short-lived, together they create a memorable rhythm overhead. Perseid meteors are known for leaving long wakes of light and color behind them. This gives them a graceful, lingering quality compared with meteors that vanish more abruptly. Their trails make the event feel especially rich and vivid to observers under dark skies. Space is full of resonances, from the orbits of Jupiter's moons to the rhythm of whole planetary systems like TRAPPIST-1. Resonance shows that gravity can create repeating patterns over long stretches of time. Instead of chaos alone, the universe often produces order, timing, and recurrence. A single moon, Europa, can stay locked to its planet, while also moving in resonance with neighboring moons. This is a lovely example of how one object can belong to several layers of structure at once. Europa is tied to Jupiter by tidal locking and tied to other moons by orbital rhythm, all at the same time. A single comet can produce both a meteor shower at Earth and its own ultraviolet auroral glow elsewhere in the solar system. That means one small, icy body can be part of multiple kinds of beauty and science at once. It can leave dust that later lights up our sky, and it can also take part in subtle, energetic processes far from Earth. And with that thought, the universe can feel quiet again, wide and patient, full of patterns still moving gently through the dark.